Good morning, my dear boys and girls. I hope you're all quite well and kindly take care of your health and studies. So in the last class, we studied about the general trends and properties of p-block elements. That is electronic configuration and oxidation state, then metallic nature of p-block elements, then ionization enthalpy of p-block elements. These are all the concepts that we studied in the last class. So this class, before starting, I want to explain a little bit about the shielding effect. So what is shielding effect? It is nothing but the decrease in attraction between an electron and the nucleus in an atom. Decrease in attraction. So if an atom contains more number of shells, you just think about the outermost electron. See the picture. In the picture, if it contains more number of shells, means the attraction between the nucleus and the outermost electron will be reduced. That type of atom will experience shielding effect because the inner shell contains more electrons. So if more electrons are there in the inner shell, means there is a repulsion between the ultimate and the penultimate shells. So these repulsion will reduce the attraction between the electron and the nucleus, between the outermost electron and the nucleus. And that is called as the shielding effect. If there is more shells are there, the outermost electron will experience more shielding effect because of the repulsion between the electrons. This concept is called as the shielding effect. Next one is electronegativity. What is electronegativity? It is the tendency of an atom to attract the shared pair of electrons towards itself is called as the electronegativity. Already you studied this concept. So now we are going to compare the electronegativity of the p-block elements. So when you move down the 13th group, the electronegativity first decreases from boron to aluminium. That is from boron. When you compare boron and aluminium, it decreases, and then marginally it increases for gallium. Then afterwards there is no appreciable change. Then when you compare the 14th group, the same trend is followed in the 14th group also. And the other groups, that is 15, 16, 17, 18, the electronegativity decreases because the atomic radius increases. So when you move down the group for 15, 16, 17, 18, electronegativity decreases as the atomic radius increases. But only for the 13th and the 14th group, the electronegativity first decreases and then increase, and then there is no appreciable change. Next is the anomalous properties of the first element of p-block. So what is mean by anomalous? Anomalous is nothing but it is different from the normal. When you compare with the normal, if something is different, that is called as the anomalous. So here in the p-block element, the first element of each group will show the anomalous properties when compared with the other elements of each group. So p-block elements will show the anomalous behavior because of the following factors. What is that? First one is the size was very small because it is the first member of that group. Small size. Then it has high ionization energy and high electronegativity because of the attraction between the nucleus and the outermost electron. And there is no d orbitals, absence of d orbital. As the size was very small, it has very low atomic number. So therefore the electronic configuration, it has the absence of d orbitals in the valence shell. So these are all the reasons for the anomalous behavior of the first element of the p-block. So in the 13th group, it's already explained that boron is a metalloid while all the other are metals. Already explained the metallic nature. And moreover, that boron, it shows the diagonal relationship with the silicon, and silicon belongs to the group 14. So already studied the diagonal relationship also. Then the oxides of boron and silicon, it is similar to the acidic in nature. Then boron and silicon form covalent hydrides, and that can be easily hydrolyzed. Similarly, except boron trifluoride, halides of both elements are readily hydrolyzed. So this is one of the anomalous behavior of 13th group. And then in group 14, as you see the picture, so in group 14, the first element carbon is non-metal, and then silicon and germanium, it is a metalloid, and tin and lead, it belongs to the metals. And in this, the first element of this group is carbon. So carbon can able to form multiple bonds. It can able to form even double bond and triple bond. And moreover, carbon has one anomalous property that is called as the catenation. Catenation is nothing but carbon can able to form a long chain compounds. That is a self-linking property of carbon. It's called the catenation, and as well as it can able to link with other atoms also. And that property is called as the catenation. So that is one anomalous property of carbon. And the catenation property, when you move along the group, the catenation property decrease down the group. Next, in group 15, the first element is nitrogen. So the 15th group contains nitrogen, phosphorus, arsenic, antimony and bismuth. In that, nitrogen and phosphorus both are non-metals. Then arsenic and antimony, it is a metalloid, and bismuth is a metal. So in this, nitrogen have the anomalous property. That is, nitrogen can able to form multiple bonds. That is nitrogen double bond N, N double bond N, C double bond N, like that, etc. Then nitrogen, it behave as a diatomic gas. Nitrogen, what is the formula of nitrogen? It is mentioned as N2, like oxygen. Oxygen is O2. So when compared with the other elements, nitrogen is a diatomic gas, whereas the remaining elements are not like that. And similarly, in group 16, the first element is oxygen. Oxygen is a diatomic gas in that group. Due to its high electronegativity, it can able to form hydrogen bonds also. Then coming to the 17th group, it is halogen, so fluorine, chlorine, bromine, iodine. These are all the elements present in the 17th group. In that, the first element is fluorine. Fluorine is the most electronegative element. So when compared with the other members of this group, it will behave in a different manner. Like oxygen, it can also form hydrogen bonds, and fluorine shows only the -1 oxidation state. Whereas the other halogens, that is chlorine, bromine, these halogens can able to form +1, +3, +5, +7 in addition to -1. It can able to form -1 as well as it can able to form +1, +3, +5 and +7. Whereas fluorine shows only -1 oxidation state. And in the halogen family, fluorine is the most strongest oxidizing agent, and it is the most reactive element among the halogens. Next topic is the inert pair effect. So first I'll explain by using this picture. You just see the picture. See, in that picture, its group name is given and its outer electronic configuration is given, and the highest oxidation state and the other oxidation state is also mentioned in this picture. First, you consider the group 13. See, actually in group 13, it contains the element boron, aluminium, gallium, indium, thallium. These are all the elements present in 13th group. So the electronic configuration is Ns2, Np1. So it contains 3 electrons in the outermost shell. So therefore, the highest oxidation state of that group is +3. So +3 is the common oxidation state for that group. And One more oxidation state is mentioned, that is other observed oxidation state, that is mentioned as +1. So when you move down the group, what happens? The most stable oxidation state is 2 less than the group oxidation state. So actually the group oxidation state is +3. If you minus 2, if you reduce 2, it becomes +1. So consider +3 as N. And the observed oxidation state can be calculated as N minus 2. Are you clear? So if the highest oxidation state is mentioned as N, so for the 13th group, the highest oxidation state is +3. That is N is +3. So what is the other oxidation state? It is N minus 2. That is, you have to reduce 2. So it becomes +1. So the other oxidation state for the 13th group is +1. So once you move down the group, when you come to bottom, what happens? If you come to the last element, that is thallium. So thallium can also form thallium +3 and as well as +1 oxidation state. So +3 is the common oxidation state of that group. And thallium can also form +1 oxidation state. So why? What is the reason? So once you move down the group, automatically its atomic radius increases. So because of that increase in size, there is an effective nuclear charge. So when the number of protons increases, there is an effective nuclear charge. So due to that effective nuclear charge, in the outermost electron, it has ns2 np1 configuration. That np1 electron alone involved in the bonding. It alone takes part in the bonding. Whereas the ns2, that is the completely filled ns2 electron, it does not involve in the bonding. It becomes inert. Therefore, it can able to form the +1 oxidation state. That inert effect is called as the inert pair effect. That is, the outer s electron have a tendency to remain inert. It does not take part in the bonding. Are you clear, my dear? I'll repeat once again. So in the 13th group, the electronic configuration is ns2 np1. When you start from boron, boron can able to form +3 oxidation state. That is, the 3 electrons will involve in the bonding. When you move down the group thallium, thallium can able to form +3 as well as +1 oxidation state. But in that, the +1 is more stable than the +3 oxidation state. Why? What is the reason? Because the outer s electron, it has a tendency to remain inert. That is, the ns2 electron will remain inert. It does not involve in the bonding. And that electron is called as the inert pair effect. And this is possible only for the heavier post-transition metals. That is, which has more size. So once the size increases, the effective nuclear charge increases, and due to the effective nuclear charge, it can able to hold the s electrons towards itself. So that s electrons, it does not involve in the bonding, and only the half filled, that is ns2 np1, that is the electron present in the p, it alone involve in the bonding. So this effect is called as the inert pair effect. Next one is the allotropism in p block elements. So p block elements show the allotropism. That is, the different forms of an element is called as the allotropes. Already you know that carbon can exist as diamond and graphite, fullerene, etc. etc. So these are all the allotropes of carbon. So here in p block element, the most common allotropes, it is given in the picture. I see that boron, carbon, silicon, germanium, tin, phosphorus, arsenic, antimony, oxygen, sulfur, selenium and tellurium. The most common allotropes are mentioned. So you just go through once. If you have the book, go through the tabular column. They may ask in one word. So carbon already you know, diamond, graphite, graphene, fullerene, and carbon nanotubes. These are all the allotropes of carbon. Then for the silicon, amorphous silicon and crystalline silicon, germanium, alpha germanium, beta germanium, tin, grey tin, white tin, rhombic tin, sigma tin, phosphorus, white already you know, white phosphorus, red phosphorus, scarlet phosphorus, violet and black. Arsenic, yellow, grey and black arsenic. Antimony, blue, white antimony, yellow and black. Oxygen, it can exist in two forms. One is dioxygen, next one is ozone. So already you know, dioxygen is O2 and ozone is O3. Sulfur, rhombus sulfur, monoclinic sulfur. Selenium, red, grey, black, monoclinic selenium, and tellurium, amorphous and crystalline. So these are all the most common allotropes of p block elements. So today in this session we'll stop up to this, and next the physical properties and the chemical properties of group 13 will be discussed in the next class. Hope you watched the previous videos. Thank you so much and take care of your health. Have a nice day.